This lecture is on geometric sequences and series. A sequence, again, is a list of numbers, whereas a series is summing up those numbers. We've looked at arithmetic sequences and series, and those are ones that have a common difference and can be modeled as discrete linear functions. Geometric ones have a common ratio between the terms and can be thought of as discrete exponential functions. And so as we see, a geometric sequence is one such that if you divide a term by the previous one, you always get the same number. That's the common ratio. So a couple examples. First, the nth term of this one is 2 to the n, so you start with n equals 1. 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, and so on. And if you divide any term by the previous one, you always get 2. Here we have 4 times 3 to the n, so the common ratio then is 3. So 36 divided by 12 is 3, and so on. And you see that whatever the base is for this general term, that is going to be your common ratio. Here we have a common ratio of negative 1/3, and this one, as you see, is alternating. The signs keep changing because every time n changes, we go from positive to negative and back and forth. Okay. Writing out the series terms or sequence terms is pretty simple. From a general term, it's a little harder doing it the opposite way. Here, another example, one more of taking some information and writing some terms. So if we start with 3 as our first term and our common ratio is 2, that means to go from one term to the next, you always multiply by 2. So to get the next term, we multiply 3 times 2, so that's 6. Then we multiply by another 2, we get 12, and so on. Finding the 15th term of the geometric sequence whose first term is 20 and whose common ratio is 1.05. Okay, well, we know that the nth term is the first term times r to the n minus 1. The reason it's to the n minus 1 is because to go from the first term to the nth term, you have to go basically n minus 1 steps. So if you want to go from the 15th term to the 20th term, in effect, you'd be going 5 steps. Now in this case, the first term is 20, so that's over here. And you want to find the 15th term, so you need to go 14 steps. So again, if you're going to get from the first term to the 15th term, you have to go 14 steps. Each step is multiplying by 1.05, so it's 1.05 to the 14th power times that initial amount of 20. This is now pattern recognition. 5, 15, 45, we see we have a common ratio of 3. 15 divided by 5 is 3, and so we'll have 3 to the nth power, say. Our first term is 5, so 5 times 3 to the nth would be too big, because if we just did 5 times 3 to the nth, we would have 15, but we want to start with 5, so we have to reduce that by 1, so 5 times 3 to the n minus 1. And then if you want to get the 9th term, well, you're just plugging in numbers. All right, the 4th term of a geometric sequence is 125, and the 10th term is 125 over 64. Find the 14th. The way I think of this is to go from the 4th term to the 10th term, you've got to go 6 steps. And so r to the 6th, as we see here, it takes you from a sub 4 to a sub 10. And so if you do a sub 10 divided by a sub 4, you get 125 over 64 divided by 125. And that's going to be r to the 6th. And if you cancel these out, you get 1 over 65 is r to the 6th, which becomes 1/2 is equal to r. So now we have our common ratio. Once we have our common ratio, we can say to go from the 10th term to the 14th term, that's 4 steps from 10 to 14. So we've got to take that 14th term and multiply it by the common ratio to the 4th power. Now we're looking at the sum of a finite geometric sequence. So it's finite, does not go on forever. This is a formula, useful just to memorize it, really. First term times 1 minus r to the nth power, where n is the number of terms, over 1 minus r. And so in this case, we have 4 as our a sub 1, r is 0.3, and n is going to be 12. So we plug into this formula. We have actually, a sub 1, is not 4. It's 4 times 0.3 to the first. So 4 times 0.3 to the first here, 1 minus 0.3 to the 12th power over 1 minus 0.3. So this is for a finite geometric sequence, the sum of it. Now, if instead we wanted to have an infinite geometric series, where we go on forever, this will only give you a sum if this common ratio is between -1 and 1. If it's not between -1 and 1, you'll get go to positive or negative infinity, or oscillate between them. But if you're between -1 and 1, you converge to this value. What happens is this r to the n goes to 0, And so this is the formula for the sum of an infinite convergent geometric series, first term divided by 1 minus r. So first term in this case is 4 times 0.6 to the 0, which is 4. Common ratio is 0.6. So 4 divided by 1 minus 0.6 is equal to 10. So if you add, this is partial sums, first term, first plus second, and third, and so on. And you can see the sequence of partial sums approaches the overall sum of 10. And here we have 3.3.03. If you look at this, you can see it's approaching 3 and a third, 3.333. And so we see the 10 thirds, 3 and a third. But another way to say it is first term is 3. Common ratio is 0.1 because you're always multiplying by 0.1 from one term to the next. So a sub 1 over 1 minus r, 3 over 1 minus 0.1 is equal to 10 thirds. And this is an application involving compounding interest, annuities, but we're going to get over to some other exercises. So here we have a sub 1 is 100. Our common ratio is e to the x, and we want to get a sub 9. To go from a sub 1 to a sub 9, you've got to go 8 steps. So you start with 100, and then you take your common ratio and you multiply it to the 8th power. So we have 100 times e to the x to the 8th power, and then power over power, we just multiply and we get 100 times e to the 8x. Here we have a sub 1 is 16, a sub 4 is 27 over 4. What's a sub 3? Well, to go from a sub 1 to a sub 4 is 3 steps. So we can say that 16r cubed, because a sub 1 times these 3 steps must be 27 over 4. So a sub 1 times these 3 steps to go from a sub 1 to a sub 4 is a sub 4, 27 over 4. Divide both sides by 16. You get r cubed as 27 over 4 times 1 over 16. Which gives us r equals 3/4 when we reduce it and cube root it. So now that we know r is 3/4, to get a sub 3, we can take the first term. 3/4 to go from a sub 1 to a sub 3 is 2 steps. So 16 times 3/4 squared is equal to 9. Here we have a finite geometric series sum. And we're going from 0 to 15, 2 times 4/3 to the n. So first term is 2 times 4/3 to the 0, so that's 2. And then we've got 1 minus 4/3 to the 16th, because 0 to 15 is actually 16 numbers. And then over 1 minus 4/3, which is approximately 592.65. And here is our formula for finite geometric sum.